All right. So yesterday, what we did, we started with the classical A polynomial. So originally that was introduced as classical, not quantum, not invariant. And it started its life as complex equation. It was nice, complex object from the start, but then, as I tried to emphasize yesterday, it should be viewed actually as object in symplectic geometry, and quantization is really just a mysterious name for modern symplectic geometry. Now, then there was this procedure which I didn't explain at all because it's a little bit astray from these lectures. I mean, if I were giving full course, of course, it would naturally belong to here. But there is a machinery which is based on complex analysis, non-commutative algebra, and so on. And in later years was nailed down in mathematical physics literature how to start with classical polynomial, say in two variables, and turn this into Q difference equation or differential operator or something like that. And it's very systematic. It takes care of all the choices and so on. But the fact that such thing exists or should exist is already essentially a premise of quantum mechanics. After all, when we start with coordinates and momenta x and p and replace p by derivative, this is the place where we start replacing essentially polynomials or various functions on a phase space by differential operators. That's the point. Differential operators, if p appears in the exponent, there'll be difference operators, and so on and so forth. So conceptually, there was nothing mysterious about what we did yesterday. We just basically followed our nose and applied rules of quantum mechanics. So these are some references, starting with the most recent one, beautiful paper of Einard and Borot, which appeared last month. Was this month, a few days ago. Then a couple of other papers, and the history goes back. So in these papers, you can find previous works on this subject. And the way it's done in practice, if you really want to do computation, it's very systematic. So this method, developed in most of these papers, is based on so-called topological recursion. This is some tool which appears in Gromov-Witten theory. Physicists call it topological string, and so on and so forth. And the method is very systematic machinery, which starts with some data of the original curve, this defined by the zero locus of this polynomial. Namely, it constructs the so-called Bergman kernel. And it involves basically complex analysis on this curve. Then, starting with that data, you produce various other gadgets which eventually, after some simple algebraic manipulations, give you h-bar expansion in this operator. So the way you actually construct this operator a hat in practice is you start with a zero term, which survives when h-bar goes to 0. And then there is a power series expansion in h-bar. But then something nice happens. Sorry, what's that question?
The relation of h and q is...
Right, so that's a good point. Indeed, q is exponential of h-bar. But then notice that most of the expressions I showed you yesterday, last time, were very nice rational functions in terms of q and x's and so on and so forth. So from this method, it would seem that you have to continue indefinitely, compute up to 15th order in h-bar expansion, and it would never stop. Then you would have to worry how to resum it. This is a very powerful method. It can, in principle, do this. But what happens in practice is that you compute first correction, second correction, and then you notice that all the higher corrections can be nicely expressed in terms of the previous one. I mean, if you know that the answer is already a rational function, so let me give a cartoon, for instance. A is of the form something like x times q minus 1 over 1 plus q squared, something like that. So here, of course, you can re-expand it in h-bar, but then you'll quickly notice that all these terms appearing in high order expansion can be nicely souped up in this rational function of q. And if you know this a priori, and this is actually what always happens in these examples of knots, what in principle you have to do, you really have to compute only the first term or sometimes the second term, and then simply check that all other ones, if you go to indefinitely high order, are essentially captured by writing the answer, a hat, in terms of q rather than h-bar. So that's the trick. to have additional information that whatever you're computing, this h-bar power series, in fact, is supposed to sum later on to rational function of h-bar. And you also know the limit when q goes to 1. You also sometimes know 1 or 2 first terms. So in practice, very little work is actually required to perform this procedure. But there is a technology, and if you want to read more about it in instances where what you produce is not a rational function, where you want to sum up the whole thing. Anyway, these papers aim to develop this more general machinery, but in practice, especially in this sort of examples, it's much more systematic and simpler. So what do we get from this? We get some sort of q-difference equation, and I write it in this particular form, changing notation a little bit from yesterday to make it more suggestive of what the result is supposed to be. And then in the homework assignment, I said, OK, this is a nice recursion relation, so why don't we try to solve it? Solve it with a natural boundary condition. It's a two-step recursion, which allows to compute object z, or now it's called j, for high value of n. Here it's clear that n should be interpreted as integer. Previously, it was just log x, and no reason for it to be integer. But since the shifts are by 1 unit, clearly it's natural to interpret n as integer now. So what we can do, we can assume that initial conditions are such that all jn's are 0 up to, in negative range. Then the first one we just normalize to be identity. That's the simplest natural starting point, and compute all the high ones. So first, you get j2. If j1 is already identity, then j2 is the first non-trivial answer. And this is actually the John's polynomial in the normalized version. If you did the first homework, that's what it is. Then j3 is also a polynomial on q, and that's what it looks like, and so on and so forth. So you continue this exercise, and what you find is that is a sequence of polynomial invariants, polynomials in q. So you get jn's all in polynomials with integer coefficients in q and q inverse. And this is the so-called n-colored John's polynomial for n equals 2. This is the usual John's polynomial. I'll say the ordinary John's. And all higher values of n, little n, not to be confused with capital N, which I used in the first lecture, these are certain generalizations which start with the same node, but colored, decorated with additional data of n-dimensional representation of SL2. So remember, previously I said that you can have quantum group invariants associated with knots and representations of arbitrary quantum groups. So in particular, you can stay with G, which is SL2, but choose any n-dimensional representation of SL2. And luckily for me, Andre, in one of his first lectures, gave us very nice review of representation theory of SL2. In fact, he emphasized that all of these representations, in my indentations there is a little shift in index n, can be recovered from two-dimensional representation. So here in my notations, dimension of Vn is equal to n for simplicity. And as a result, what happens is that if you know how to compute the John's polynomial, and I explained it to you in the first lecture, namely one can use kind relations, that's perhaps the simplest and the most straightforward rule, you can actually adapt this rule to compute all of these higher values of colors or high dimensional representations. And so the corresponding quantum group invariant is exactly this Jn. Yes?
And so the alpha, beta, and gamma are determined by the nodes?
Right. So the logic here is as follows. This was, of course, same example of this trefoil knot. So in general, there could be many alphas, betas, there could be coefficients AI. And let's see, we started with a knot, which determined for us first a classical A polynomial. That was just, by looking at representations of knot group into SL2. Then there is this mysterious machinery, which luckily is very systematic, but goes by this mysterious name of quantization, which turns this into a difference equation. And then you solve the difference equation and you find the whole chain of quantum group invariants. So all of this is determined by the knot. And this is the bridge between two types of knot invariants, which until recently were studied by completely different groups of topologies. There was a group, in fact, center of mass of it probably is here around Chicago area, which focused on these curves, these polynomials. And then there is, of course, a much larger group which studies quantum group invariants for different nodes, groups, representations, and so on. And until very recently, they didn't even talk to each other. They had no reason to talk to each other. But this provides a nice link between these two areas. So in fact, what happened is for us in this discussion, we managed to find the same answer for infinitely many, if you wish, quantum group invariants associated with different representations, different colors, just from one simple recursion relation. So in some sense, this recursion relation, but it comes from the simple curve or polynomial, encodes a lot of information. It encodes the whole tower of such quantum group invariants. And we didn't have to talk much about quantum groups. Of course, there is some theory behind it which explains why it works. But in these lectures, I decided to explain how it works and hide the fact why. So next week, I'll give a talk here at the conference, and I'll try to shift the emphasis, maybe say a little bit more about why it works, but I decided here to focus rather on computational aspects. So show it to you that it's...
You have two knots having the same A polynomial.
Yes.
Do they have the same higher Jones polynomials?
Excellent question. In particular, if everything I said is correct, it implies that the answer is yes. And I don't think that this is a theorem, although it could be at this stage, but at least I assure you that in all cases where it's been checked, for all knots with up to, say, 15 crossings or 20 crossings, that's the case. So it's indeed, basically, your question implies the following. It says that if this procedure is unique, or if every step here is systematic, as I advertised it, then it means that the whole collection of so-called n-colored Jones polynomials is no stronger or no weaker than the A polynomial. And that's indeed the case. So that's what it means. In particular, previously I showed you some examples of knots which could not be distinguished by Jones. I don't remember which ones I chose, whether they could be distinguished by color Jones, but in any case, as I say, it always comes together. So anything that can be distinguished or not by A can or not be distinguished by J. So this is this story. Okay.
If that's the case, I'm not sure why we care about the colored Jones polynomial.
I'm not sure either. No, of course, serious answer is that historically, quantum group invariants were discovered first. So there is a priority issue here, and also by important people. So you can't just forget that. But again, I'm just joking. Well, see, I did a mistake of not emphasizing how quantum groups enter quantum group invariants. And I think it's an honest mistake, because this is a beautiful part of the story. Unfortunately, if I were to dwell on it, we would not be here today at this stage. So it's really amazing that something which has to do with quantum groups, R matrices, and all that stuff has same information as algebraic curve. So that's indeed surprising. But there is a lot more to be understood here. So don't take this as done deal and story which is finished, should go to textbooks, and that's it. There is not much to do here. Actually, there is a lot to do. In fact, in the answer to the previous question, I mentioned that I'm not sure whether this is a theorem or not. So there are lots of statements that, even though they come from mathematical physics, are currently under consideration, and some of them being proved, some not. So there is a lot to be done here. And of course, even if all of this unifies in the end, it's still interesting that we have two different definitions or ways to enter the same data. One from this representation varieties, the other from quantum groups. And admittedly, this is more complicated. So at least that's what it looks like. Okay. So I gave you the answer to homework from yesterday. Let me also give you the answer for homework from first day, the very first day. So here we have, question was, what's the Homfly polynomial of the trefoil knot? And I asked you to practice several computations with different normalizations and so on. So let me just summarize the answer to illustrate what it looks like. The original, most straightforward, unnormalized version, when you don't divide by anything, when you don't have to worry about which components to normalize and so on, is what we call unnormalized. That's where Homfly polynomial of the unknot was a minus a inverse divided by q minus q inverse. Okay. So then this guy goes for the ride for all other knots. In particular, if you do this homework for the trefoil, you find that P of the trefoil is this times another piece, which is a squared q minus 2 plus a squared q squared minus a to the fourth. Okay. So therefore, if you try to compute what's so-called normalized Homfly polynomial, where P of the unknot is just identity, you would naturally divide by this factor. And what you get is the remaining piece here, which is simply a squared q minus 2 plus a squared q squared minus a to the fourth. Okay. Or, and I'll put all answers on the blackboard, sometimes people use different conventions, in particular scaling all these degrees by a half. See, everything here involves even degrees, therefore perhaps more economical notations involve halves of this, and that's what people sometimes use. So another expression that you may encounter could look as follows. It could be a q inverse plus a times q minus a squared. That's another acceptable answer. So all of this, if you scan through literature on knot theory and ask a given author of a given paper, what's his convention for trefoil, or what would he have for trefoil knot, the Homfly may have one of these three forms. You'd find one of these three expressions. So in particular, I told you that Homfly has this nice feature that it's a polynomial in a and q, and if you're specialized to a equals q squared, you're supposed to find the Jones polynomial. And just for fun, let's see what we get from here. If a is equal to q squared, then this expression would give us Jones is what we call J2. So for the trefoil, in these conventions, we would have, let's say, q plus q cubed minus q to the fourth. Okay. Same as that guy. Okay, so next thing is categorification. In different cases, categorification means different things. And to me, this is a feature, not a bug. It's like an art where there is no unique answer. There may be several different categorifications, and the way they proceed depends on which structures you want to emphasize in your given problem. So that's why, again, my friend Roman Bezrukovnikov sometimes says that categorification is like a geometrization. You have an algebraic problem to which you want to find geometric home or geometric framework where it could be realized. And I hope with examples of moduli spaces last time, I illustrated a little bit what kind of geometry could sit behind concrete algebraic expressions like any of this. But in the context of low-dimensional topology, categorification usually means something very specific and very concrete. In particular, if you deal with n-dimensional TQFT, such as 3-dimensional TQFT, which we're discussing so far, then categorification means somehow upgrading the theory to a higher dimensional TQFT. So if you have 3D TQFT, upgrade to 4D TQFT is what would be naturally called categorification. It's basically finding a theory in one dimension higher such that upon dimensional reduction, it would give you the previous one. So that dimensional reduction is a simpler procedure. It's very systematic, and that's sometimes referred to as decategorification. In particular, last time we had this dictionary between geometry, classical theory, and quantum theory. So today, yesterday I made this emphasis on distinction between classical and quantum. Today I'll just summarize these rules as they're usually stated without such emphasis. So geometry and simply 3D TQFT. And we know that to a 3-manifold, which we usually call M, and M may come from a knot. So I could also say that to a knot K, or perhaps not K even sitting inside M, or perhaps some combinations of knots and 3-manifolds. 3-dimensional TQFT associates a number of some sort. It could be a number, or in view of yesterday's discussion, wave function. So something like Z of M, or P of K, where P is a polynomial of a knot, and things like that. Okay. So this is what we have in 3D TQFT, and to 2-manifold, just to continue one level down, we associate a vector space, which is the space of conformal blocks in the context of Chern-Simons theory. Now, if you were in 4D TQFT, 3-manifold would be codimension 1. It would be much like 2-manifold in Riemann surface in a 3-dimensional theory. And therefore, to a 3-manifold, you would actually associate a vector space if you had 4D TQFT. So this vector space H could be, again, labeled by this 3-manifold, or if 3-manifold is a knot complement, by the knot, or various other data that you have. Likewise, one level down, 2-manifold now is codimension 2 from the viewpoint of the 4-dimensional theory. So 4D TQFT would associate to a 2-manifold a category. I hardly used any categories in this lecture, so I don't think I have to introduce any notation for that. So if I were, I guess I could call it cat sigma or something like that. So what categorification does, it does this upgrade from lower categorical objects to higher categorical objects, and in particular associates vector spaces to 3 manifolds with knots, or just 2 knots, if 3 manifold is a 3-sphere, and categories to 2 manifolds, possibly with marked points. So since these aspects have been discussed in detail in other lectures, I guess this is easy part of the ride, and I don't have to spend too much time on this. Now, I want to put a couple of things in perspective for you and connect now what we're discussing here with the previous lectures, and in particular with the first lecture. So there I gave you the definition of the Jones polynomial. Usually we denote it by J of Q, and as I mentioned here, it actually can be generalized to so-called the scalar Jones polynomials if you replace 2-dimensional representation by n-dimensional representation, and they're also computed by simple combinatorial rules. And for us, the Jones polynomial came as a special case of a more general invariant called the Homfly polynomial. So we call it P of A and Q, and in fact the example is just here on the board. So specializing to A equals Q squared kills one of the variables. In fact, to emphasize how these things depend on variables, let me write them in yellow. So this will be A and Q. And the point is that 2-variable polynomial with a particular specialization gives you yet another not invariant. Now, if you were to categorify the story, what it means is that you would replace Jones polynomial by vector space. And I'll give you a couple of definitions in just a minute. But this sort of upgrade is a generalization of Jones in a different direction, which then can give you Jones back, and is known as Khovanov homology. So let's call it H, or I'll just call it KH for Khovanov, Khovanov K for simplicity. And likewise, Homfly polynomial has its own categorification such that polynomial can be obtained from this theory. It's called Homfly homology. And somehow they fit in this big diagram, which I'll try to make a little bit more explicit. And in the rest of my lecture today, the goal is to say something about these homological objects obtained by categorifying the corresponding knot polynomials. So assuming that we already understand to some extent relation between these polynomials, where one depends on one variable, the other depends on 2 variables.
So may I ask you
Sure.
why that is called like categorical?
Well, the name refers to the fact that you're promoting each gadget to one categorical level up, to higher categorical level. So for example, here, if I go to the next stage, to 1 manifold, TQ of T in 3 dimensions would associate a category. But following this rule, it would actually associate a 2 category in 4 dimensions. So in some of the 1 and 2 categories that we discussed, in particular that you referred in Chris's lectures, have to do with such structures in 4D TQFTs. Any other questions? Right, so you're, in 4D to QFT you have also one level up, which I am not indicating where 3D to QFT is, but there is also a 4 manifold. So to 4 manifold I would associate a number. To 3 manifold we associate a vector space. So that's why I try to draw them on the same line, kind of in parallel. But for 4D to QFT you can actually go a little further because there are also 4 manifolds. And to them you associate numerical invariants such as Seiberg-Witten or Donaldson, things like that. But in all of these theories, you can certainly go down, and that's where you encounter higher categories. And again, I should probably emphasize that in all good theories or sensible theories which come from PDEs, in particular in Donaldson theory, Seiberg-Witten theory, and all of those variations, you have some geometry. So all of these categories, 2 categories that you encounter, they come from some moduli spaces, from some geometries. For example, a category that you would encounter in Seiberg-Witten theory is actually Fukaya category of some space, of certain symmetric product and so on. So, okay. Now, coming back to something more concrete, right, I'm supposed to explain these 2 corners because, again, polynomials are already familiar to us, and I'll explain a little bit about behavior of these homology groups. So Khovanov homology is associated to Lie algebra SL2 and 2-dimensional fundamental representation of SL2, much like the Jones polynomial, and it has 2 gradings, I and j, such that first it has some definition and so on, but one of the properties of this theory is that the Jones polynomial, which we call J2, or I can also denote it JSL2V2 because that's where it comes from, can be recovered as a graded Euler characteristic of this theory. So very concretely, taking a weighted sum with weights -1 to the grading I and Q to the grading J, and then writing here dimensions of Hij, we recover the Jones polynomial. So the idea here is that to every knot k, you associate these doubly graded groups. And Jones polynomial can be obtained by taking the Euler characteristic. In particular, if you have doubly graded groups, it's convenient to introduce Poincare polynomial, which this time will depend on 2 variables. So it will depend on Q, and also I'll introduce another variable T. So it's basically the same sum over I and j, T to the I, Q to the j, and then dimension Hij. And even though it's a little bit cheating and actually defies the purpose of introducing homology theory rather than polynomial knot invariants, it's sometimes convenient to denote, to encode information about homology into dimensions of these groups. So in particular, this Poincare polynomial sometimes is a good approximation to the story. So in this corner, I guess I could write this Poincare polynomial of SL2 theory associated with two-dimensional representation. That's exactly the Poincare polynomial of Khovanov homology. And it depends on two variables, Q and T. And the specialization to Jones in this language is obtained by taking T to be -1. Okay. So, for example, just for fun, in the case of trefoil knot, which is our prime example, this polynomial PSL2 V2, which is Poincare polynomial of Khovanov homology, for the trefoil, and in normalization, which I used last, namely where we got this sort of Jones polynomial, we have Q squared plus, sorry, Q plus Q squared, sorry, Q cubed T squared minus Q to the 4 T cubed. So in particular, you can easily see, since that formula is still on the board, that specializing to T equals -1 does give you the Jones polynomial. And in this case, what you would say is that Khovanov homology has dimension 3, and it has 3 generators sitting in Q degree 1, 0, 3, 2, and 4, 3. Okay. Again, I'm not giving you the definition, because if I have time, I'll tell you a shortcut how to get the definition or bypass it. Okay, very good. So then, since Homfly polynomial is on this board, let me go on and say a few words about analogous homology theory that categorifies Homfly polynomials. So we go along this arrow. So Homfly homology is somewhat, it does a similar job, but it has one slight difference. It's also a theory which we associate some knot invariant, homological knot invariant, which we associate to the knot, but it carries 3 gradings, I, J, and K, and has the property that our familiar friend, namely the polynomial, is obtained from this triply graded theory, now it's triply graded, by collapsing one of the gradings and summing with weight -1. So this is sum over I, J, and K, -1 to the I, Q to the J, and A to the K of dimensions of H, I, J, K. And of course, again, if you're interested in dimensions or want some quick ways of encoding the information, it's convenient to introduce Poincare polynomial. I'll denote it by this script letter P to emphasize that we went to a fancy world of homologies where H's themselves are kind of calligraphic, so therefore it will be script P, but I'll use also color chalk to emphasize dependence on various variables. So in this case, we have 3 of them, and then encode this 3 gradings on H, I, J, K. T to the I, Q to the J, A to the K, dimension of Hij. So in that same language, if I write here this Poincare polynomial P of A, Q, and T, which more or less captures all the information about homology theory except for torsion, then specialization from here along this arrow is also obtained by taking t equals -1. And you expect that specialization in this direction for diagram commute should be A equals Q squared. So there are these different specializations. Which relate now all of the objects that we introduced and polynomials we saw in practice and homologies or some vector spaces which, if you care only about dimensions, could also be stated in terms of polynomials. Yes?
So if you put A equals Q to the n, then you also get the expected answer?
If you get A equals Q to the n, you are expected to reproduce something about SLN version of this homology, where again it's some SLN theory colored by fundamental representation of SLN. But I want to say that all of these boxes, which I put in blue, all of the specializations are okay. So everything I said here holds true verbatim for this specialization, this one, and this one. And this fellow here requires a little bit of discussion. And my remaining 10-15 minutes will actually be devoted to that specialization. So it's a little bit more subtle than I just said. But again, let's go in stages and iteratively build more advanced knowledge based on simpler facts. Roughly speaking, that's what should be for the diagram to commute nicely. Okay. Now, the reason I'm telling you about all this in these lectures is that it turns out that each of these objects has its colored version, just like Jones polynomial has its color generalization associated to high dimensional representations. Homfly polynomial does so as well. So in fact, there is a version of Homfly polynomial colored by high representations or interesting Young tableaus. Then all of these guys have categorification. So there is a colored version of Khovanov homology and also colored version of Homfly homology. And fun thing is that just like color behavior of color Jones was completely captured by algebraic curve, namely this A polynomial, these theories, their color dependence also is captured by some algebraic curve, which is either A deformation or T deformation of our A polynomial. And then there is this most advanced object, which is Homfly homology. And it turns out that these polynomials, there are also n analogs of them, also obey recursion relations. And again, their dependence on n is captured by deformation of the A polynomial curve, which now depends also on A and T. So there are these fancy deformations. I'm not going to talk about this here because, again, I'll explain this more next week. And I think understanding one basic example, which we did in detail involving Jones polynomial and its colored version in the previous lectures, is good enough. So instead, even though, again, in some sense, this is the most exciting thing, it's pretty advanced, and conceptually it follows much of the same steps as we already did in the previous lectures. So what I'll try to do instead, I'll spend remaining 10-15 minutes giving you a little bit more insight into how these homology groups look like. And they're not scary at all. So computing them sometimes is easier than polynomial knot invariants, or at least not harder. So that's my goal, to explain how to compute them in very practical terms. Yes?
Does Homfly homology give a complete invariant of knots? Or?
No.
So can you imagine like this vision where you categorify that further and maybe hold something there?
There is always hope, yes. No, seriously, yes, of course you should. So it turns out part of the reason that people are interested in homology theories that they capture more delicate information about the knot. Of course, a homology of a manifold has more information about the space than earlier characteristic. And homology does help to distinguish some knots which are not distinguished by Homfly and Jones. So the serious answer to your question is that it's already doing a good job. It misses a little bit. Sometimes it doesn't distinguish knots which are really close to each other, such as mutants, for instance. Sometimes they're missed. There is a phenomenon called knot mutation, which unfortunately not always is captured by Homfly homology, but then passing to this colored version usually nails it down. So that's already pretty strong invariant. But then, of course, one can hope that somewhere in this world of categorification, there is indeed a complete invariant of knots. So that's actually, serious answer is that's motivation for many people who are working on this and who invented these homologies. Okay, so to demystify some of these relations, which are quickly proliferating, and again, illustrate definitions and examples, let's look at what happens very concretely in the case of the trefoil knot, which has been and still is our main example. So what do we know about the trefoil so far? Thanks to all the homeworks and everything we're discussing, we certainly know Jones. So Jones is q plus q cubed minus q to the fourth, and depends just on q. So I'm just trying to reproduce that diagram in a very concrete example, which repeats much of the facts we know. I'm just collecting them on the same blackboard. So then we also know Homfly, p of a and q. Here, the second variable makes its appearance. And it was somewhere here, yes, here on the board. It's q plus q cubed t squared plus q to the fourth t cubed. And indeed, it has an obvious property that specializing to t equals -1, we recover this guy. So it deserves to be called categorification. Oh, sorry. That's Khovanov, right? I should have put it on this side. Perfect. Thank you so much. Thanks for right drawing my attention. So in fact, q and t gives us this. Yes. So q plus q cubed t squared plus q to the fourth t cubed. Yes. So it should sit on this side. And let's see, where is Homfly? Do I still have it on the board somewhere? Well, anyhow, I'll just read it off again from my notes. So it's a times q inverse plus a times q minus a to the fourth. So far we, square. So far we have these results, and they indeed work out nicely. So if I specialize to a equals q squared this direction, I indeed get polynomial here. If I specialize to t equals 1 minus 1 in this direction, I get, again, the Jones polynomial. And then you see something pretty obvious, that if you're trying to invent an invariant, the script p, which depends on 3 variables, A, Q, and T, there is almost no choice but to say that it should have 3 terms, because at least all of these specializations have exactly 3 terms. And you can view the problem in either trying to restore T dependence in this guy or A dependence in this guy. And again, it's very easy to complete this exercise. So basically what you find is that it's A times Q inverse T to the 0. Because see, each of these terms specializes very unambiguously to terms in different degrees here. And therefore, if you know what was their T degree, you can essentially restore it here as well. For instance, the term Q in the Jones polynomial comes from AQ inverse, if you specialize to A equals Q squared. And that's the guy which has no T dependence in categorification. So it goes with T to the 0. Same with the term Q cubed. It comes from A times Q, and it gains T squared dependence in categorification. So, OK, we'll just play this game and write A times Q T squared plus A square times T cubed. So if you wish, here is the answer. And we got it just by sort of guesswork. In this case, it was inspired by consistency of everything. But it actually is the correct answer. So if you go ahead and use all the definitions, which I didn't spell out for you, do the computation, that's what you recover. But now you immediately gain something. We only used input here of polynomial knot invariants, which are easy to compute. We already talked about this homework in the very first lecture. So this is easy, way easy, skein relations. Khovanov homology is somewhat a little bit more non-trivial, but it's also combinatorial. And we use that as the only other input to get the whole Homfly homology, the triply graded theory, which now packages not just SL2 invariants, but in fact all SLN categorifications as well. So this is a very powerful invariant. And somehow what we did, we saw the pattern here, that specializations are consistent, and we use them in this way to restore the answer. In fact, what you could have done, you could have obtained this answer even without knowing Khovanov homology. So that's the fun part. So here we got our leg, our foot in the door of categorification by knowing T dependence here. And it seemed like an obvious thing to combine this information and produce the answer. Surprising thing is that you can get that answer without even knowing Khovanov homology. So let me explain to you how you do this, and then I'll stop. So first, however, let me picture the answer that we just produced on the top of the board in a diagram which represents the Homfly homology. So H Homfly will be represented by this diagram where we have, where I'll show explicitly the Q degree on horizontal axis and A degree on the vertical axis. So everything happens in A degree 1, 2, or in Q degree -1, 0, and 1. And first thing that you can do as a starting point is try to picture on the diagram the terms which already appear in the Homfly polynomial. So there are 3 terms with AQ inverse, A times Q, and A square. So I'll picture them with the dots in this diagram. Categorification, so this picture encodes terms in Homfly polynomial, and categorification of this picture means assigning T degree to each of the terms. That's essentially what it does. And the answer that we found is that T degree of this term is 0, T degree of this term is 2, and t degree of this term is 3. Okay. So that's the same answer, just represented pictorially in this diagram. Now, let me come back to something that was also part of the first homework. So now we're collecting the dividends. And the last piece of information or homework that I asked you to look at was the following. I asked, take a look at what happens when you specialize in the Homfly polynomial to a equals q. Okay. Something nice happens. So let's see what happens in this example. If a equals q, this is 1, this is q squared, and this is also q squared. Okay. So the Homfly polynomial in this case reduces to a single monomial. And in fact, this is true not just about the trefoil knot, but for any knot. And this is true for a very basic reason. Remember that specialization to a equals q to the n corresponds to SLN, quantum group invariance. Therefore, a equals q means SL1. And SL1 theory in every world is trivial, right? So therefore, quantum group invariant of any knot associated to something trivial should be trivial. It should be probably just identity, or maybe if you use some shifts and various degrees, single monomial. Okay. Correspondingly, SL1 homology should be also trivial. So in fact, let me replace this diagram by something more general and write here SLN and Vn, which is something we already discussed. So this is not Khovanov homology, but rather SLN homology now. Simple generalization of this discussion. So in any world, SL1 should be trivial. And in some sense, that's what we're witnessing, that specialization to a equals q gives you trivial quantum group invariant. But what about its categorification? What happens here at the level of Homfly polynomial, you see, because it has minus signs, various terms cancel each other neatly. And I claim that no matter which knot you try or which link you try, you'll find the same phenomenon. That there'll be lots of cancellations, and it will reduce every Homfly polynomial. If you put a equals q, will reduce to something boring. And how on earth this property can work at the level of this diagram? So this is not going to be Jones, but something like Pn of q. Again, this is just SLN. Before we set t equals -1. So this is hard to achieve if your polynomial has only positive coefficients, such as Poincare polynomial of something. It has no negative coefficients. And obviously, if at this stage you set a equals q, you'll never get something one-dimensional, something trivial. It just won't happen. Okay? So that's already one hint that something is fishy about this box, which I mentioned earlier. Moreover, here there are two analogous properties. There is this one here, and actually in the Homfly theory there is a corresponding property where you set a equals q inverse. You also find just a single monomial, and it has to do with a symmetry which, roughly speaking, switches the n or takes q to q inverse. So you can play with this expression and see, I don't have time for it, that such specialization also gives you something trivial, something boring. Okay. So let's think what could possibly be the right answer or the meaning of this arrow, the specialization. So that's the last thing I have to explain. Here, once we categorified this, upper part of the diagram involves homology theories, involves vector spaces. This is a triply graded vector space. This is a doubly graded vector space. Using Poincare polynomials was just a crutch to get some information out of it, to encode it. For example, if you want to write recursion relations, yes, polynomials are useful. But this is not why we categorify things. These are homology theories. And the claim is that here, this relation, specialization to roughly, which is trying to be a equals q to the n, is obtained first of all by collapsing the grading, which is consistent with a equals q to the n, but then also by taking differentials or homology, viewing this theory as a complex and taking homology with respect to certain differentials. So instead of explaining the definitions and so on, let me just draw them here on the picture. There are two differentials here, which are called d1 and d minus 1. So this is d minus 1 and this is d1, such that if you use this dot diagram as a complex and take homology with respect to differential d1, which takes this generator into this generator, you get something one-dimensional. Likewise, there is yet another differential such that if you view this diagram as a complex and take a homology with respect to differential which takes this generator to this generator, you're also left with something one-dimensional. So statement is that this is the proper homological upgrade of these simpler specializations of these properties. So more generally, statement is that this triply graded homology Hij is equipped with differentials dn, which can be greater or equal than 0, and dn for negative values of n, such that they have degrees -1 and -1 and -1 and -3. These degrees are not mysterious and they don't come out of the blue. In fact, the relation between a degrees and q degrees, which are in the first two spots, has to be there. So this refers to a degree, q degree, and t degree. It has to be such that q degree is roughly minus n times a degree. This has to be consistent with specializations to a equals q to the n. I don't have much time to explain it, unfortunately, but that's where it comes from. T degree for any normal differential is usually -1 or +1, depending which way we orient things. So any normal differential changes t degree by 1. So at least for positive guys, which are really normal, that's the case. And this conventions, strangely enough, the other fellow turns out to have degree -3. Now, these differentials are supposed to produce these specializations to SLN invariants and kill the terms which otherwise would be removed by minus signs if you have t equals -1. Of course, before you set t equals -1, this is impossible, and you have to have these guys. Now, the statement is that they exist for all knots, and they indeed take you from more advanced Homfly homology, triply graded theory, to doubly graded SLN homology. And if you know that these differentials exist for every knot, you don't need to know anything else to recover the whole theory. For example, going back to our previous discussion, suppose I put dots here by knowing terms in the Homfly polynomial, and I want to restore the t degrees. Then I know that I should have two differentials for n equals +1 and -1, which should give something trivial, because SL1 is trivial. One differential is d -1, it's acting this way, and on this diagram I see only two terms which could be killed by this differential. And I also know that this differential has difference in degrees -3. So it immediately tells me that t degree of this generator has to be 3 if I assign this guy to be 0. Likewise, I know that differential d1 has to give something trivial, again, because SL1 is trivial. And it acts this way on the diagram with respect to a and q degrees. It lowers a degree by 1, increases q degree by +1, so it acts this way. And it also changes the t degree by -1, lowers t degree. So if I already assign this fellow to have t degree 3, this guy should have t degree 2. We're done. See, this is kind of tricks, and these differentials proliferate and become a very nice cohesive structure, which completely determines not only uncolored Homfly homology, but in many cases even colored Homfly homology and various other theories. So this is just a tip of an iceberg, which, as you see by itself, allows to reconstruct the answer based on these structural properties. So this is kind of preview of something that I'll mention in more detail next week. So I think I should stop.
Yeah, thank you very much. I'm sorry to say that Sergei has a cab waiting for him, so we won't be able to have a discussion at this point. However, Sergei will be back next week for some days, so those of you who are sticking around will have a chance to talk with him at that point. Let's thank him again for this wonderful lecture.